Hi, good afternoon. I'm Jose Andres, and this is my case study analysis. Now, what did we work as a case study? We worked the analysis of the motion of a bungee jump through differential equations, basically. What should we consider? Firstly, we have to understand that in a bungee jump, the two forces that we'll be considering will be the weight that's pulling the body downwards, or therefore it is negative, and the elastic force, which is contrary to the weight, which is positive. Well, it ends up being positive. Now that we understand that, we go to the phase one because it is divided into phases. It's since the body starts falling to it when it reaches the chord's length, and when the chord's length is reached to the elongation of the chord. So for the phase one, it is basically the force is just the weight, so it is ma equals minus mg. We cancel the mass, of course, and we integrate two times because the derivative of the position is the velocity, and the derivative of velocity is acceleration, and vice versa with integrals. So we integrate two times, obtain our position function. We do so, and we get this formula. This is the initial velocity, of course. We do so once again. All of this is done with the separation of variables method, and we get this formula that we all worked with in physics. And that's how we do phase one. Now, for the phase two, since there is the hook force or elastic force pulling the body upwards, it'll be positive. The gravity stays negative. Time is reset because it'll help us later on, and we can rewrite like force like this because it is the acceleration, the second derivative of the position. However, it is negative because it's trying to stop the downward movement of the body, and it's decelerating. So this is how our formula would look like. We play with our formula a little bit. We move all of our elements so that the formula is positive, and we can define Hooke's force as ky, because in our reference frame is the chord's length. It is zero at the beginning of phase two, and then the y, it's just the elongation. Now we cancel m, where it goes on dividing, and we can cancel m here, but here we have a k over m, which we know means or is equal to the angular speed to the squared, because angular speed is k over m, but in a square root. Now, this is our formula, and we can integrate. However, it is not a homogeneous equation, so we have to have the particular solution and the homogeneous solution. So the particular solution is this one, minus mg over k. It is a high order linear differential equation, so we do what we learned in class. The second derivative is m squared, or alpha in this case, and the angular speed to the squared stays the same. Now, we know that our root would be negative, so we use this formula. And now this is the final formula for the position in this case. However, we also would like to obtain the velocity one because it will be helpful for us. And now we substitute. Since time is zero, the cosine will equal 1, sine equals 0. So we obtain these equations. We can clear for C1 with this and obtain that C1 equals mj over k, g over k, and the c2 equals the initial velocity at the second phase over the angular velocity. And since we know that the initial velocity at phase 2 is the final velocity at phase 1, we can go to phase 1, substitute for the time in this formula since initial velocity is 0, and then substitute once again in the velocity formula, and we get that velocity equals minus square root of 2 times the gravity times the chord's length. We substitute once again now in the C2 formula, and we obtain that C2 equals minus square root of 2 times the mass times the gravity times the chord's length over the elastic constant, and we substitute in our formulas. That's how we do all of this. That's how we can obtain the position formula for the bungee jump. And what we can do the further we can go is substituting our data. My mass is 75 kilograms, so I put all my data here, and we can just substitute, but we can go any way further because the function depends on time. But yeah, this is it. It was a really interesting project, case study to work on, because it really was good mixing math, physics, and real life problems. So it was really good, and yeah, good project.